This is a biomechanics of movement study. No declarations. Only about 1 in 10 low back pain patients are able to identify the cause, and this really highlights the need for further modeling studies to figure out what's going on under the hood. And in the workplace, faster lifting has been linked to greater incidence of injury, and yet most finite element studies have investigated only static flexion. We have built a comprehensive finite element model of the spine and trunk to study intra-abdominal pressure, or IAP, in transient conditions. IAP is the pressure contained within the abdominal compartment and is proven to have large transient variations during lifting. Our aim was to study the effects of movement speed and high IAP on spine stability during movement. In our modeling approach, we focused heavily on physiological accuracy, creating what is, to my knowledge, the most anatomically realistic model of the abdominal compartment. A series of integrated tools were used to develop the model, starting from MRI segmentations of a young, healthy male to study the baseline biomechanics. The simulation was run in ANSYS transient structural using nonlinear and viscoelastic properties. The model was validated against in vivo, ex vivo, and in silico data. Here we see, for example, very good alignment of intervertebral disc pressure plotted as a function of pure compressive forces. We also compared intervertebral rotations against cadaveric testing. This is plotted here at each level against applied flexion moment. And again, we see very good alignment for every level with the possible exception of L4, L5, though we do see in the next graph better alignment with in vivo rotation patterns. For the study design, we bring all this together, starting by statically pre-stressing the spine into a flexed posture from which a worker might begin lifting a box. In combined compression and extension back to neutral standing, 6 load cases were simulated for 0 and high IAP at fast, medium, and slow lifting velocities. During the movement trajectory, a dynamic perturbation was applied, and stiffness was evaluated as the angular deviation from the baseline unperturbed trajectory. Here we see plotted the lumbar stiffness for each of those 6 load cases. IAP appeared to limit displacements, acting like a shock absorber to destabilizing forces. The effect was similar at all the load rates, though we do see the largest gain from IAP of 33% at fast velocity. And this is meaningful since we know that forces on the spine are greatest in fast lifting, and we show here that the intrinsic stability potential from IAP is maximized. Essentially, IAP can create passive stability when displacement limiting is most needed. Here we've isolated time curves during the perturbation event. On the left, we see that when moving faster, the spine was stiffer relative to its angle at the time of perturbation. However, we're measuring stiffness relative to the target trajectory, and this deviation from target is plotted on the right. The solid lines represent 0 IAP load cases, and we see the effect of IAP, the dotted blue line, was to attenuate the peak by about 30%. In other words, the effects of IAP on intrinsic stiffness appeared to be greater than that of movement speed. Every model is a balancing act between computational cost and engineering assumptions, and this was especially true given the large deformations and transient nature, which unavoidably extends computation time. Favoring cost reduction, an adaptive mesh size was used throughout the model, but sensitivity analyses were done proving that the discretization was sufficient. Finally, by directly controlling IAP, it was decoupled from abdominal muscle activation, and this ignores some force pathways for stability, focusing on the buttressing and offloading effects. However, we expected that those ignored pathways would have just amplified the results shown here. Some points to remember: the virtual twin case control study showed that IAP provides dynamic stability potential, acting like an airbag to limit displacements. And the relative importance of this effect was greatest. The relative importance of this effect increases with movement speed. And this stability potential could be accessed without added physiological cost by external orthoses or with training targeted muscle activation. Thank you to all the contributors, especially my supervisor, Professor Mark Driscoll.